Now, what about the volume of solid of revolution? So, let me explain the concept. So, we are asked here to find the volume of the solid generated by revolving the area bounded by the circle x squared plus y squared is 4. The circle x squared plus y squared is 4 may be written as 2 squared. This is a circle whose center is at, equate this to 0, x is 0, equate y squared is 0, so this is 0. The center is at 0, 0, and this is r squared. R is equal to 2. So, this is your y-axis and this is your x-axis. This is 0, 0, the center. The radius is 2. That is the circle whose radius is 2. And let me repeat, the center is at 0, 0. Okay? It will be revolved about this line whose equation is x equals 3. It is 3 units to the right of your y-axis. So you revolve this area about this. So to draw that figure, let us draw the mirror image of this circle on the other side of the axis of revolution. So that mirror image will be this one. Okay? Then you revolve this. The volume that you will be generating, or the solid that you will be generating, is a donut. Or the technical name for that is a torus. Now, according to Pappus Theorem, the volume of that solid of revolution is equal to the area of the surface revolved multiplied by the distance traveled by the centroid of this. Since you revolve it in a circular path, the distance traveled by the centroid is a circle, like this. The centroid is this. When you revolve it about this centroid travels this much. So the distance traveled by it is the circumference of the circle, whose radius is the distance from the centroid to the axis of revolution. Let me call this as z. So this distance traveled by the centroid is 2 pi z. Z is the perpendicular distance of the centroid of the area from the axis of revolution, which is actually the radius of the circle. Okay? Radius of the circle generated by our centroid. So, in here, the area of the circle is pi r squared. The radius is 2. This is the area of the circle times 2 pi. And our z is 3. Okay? So, this is 3. So, therefore, this is going to be 4 times 6. That is going to be 24 pi times pi, pi squared cubic units. So, this is the volume of that torus, or volume of the donut. Okay? What about if this is the problem? Find the volume of solid generated by revolving the area bounded by y equals x cubed and x squared equals y cubed about the y-axis. First, for plotting purposes, let us solve the points of intersection. We can do that by substituting the equation 1 to equation of curve 2. So we have here x squared equals y cubed. This is from curve number 2, this one. You substitute y is x cubed from curve number 1. So I have x squared is equal to y. What is y? X cubed from curve number 1 cube. So this is x to the 9 equals x squared. So what we will have will be x to the 9 minus x squared is equal to 0. We just factor out x squared. What we will have will be x to the 7 minus 1 is 0. This times this is equal to 0. So equate both sides of both expression to 0. X squared is 0. So x is equal to 0. And x to the 7 minus 1 is 0, so x will be equal to 1. These are the x coordinates of the points of intersection. But knowing that y is equal to x cubed, so when x is 0, y is equal to 0 cubed, 0. When x is equal to 1, y is 1 cubed, so y is equal to 1. Your points of intersection are 0, 0, and 1, 1. Right? So let us try to plot them. But to be able to plot a curve, these are curves, not merely lines. You need at least 3 points. Let us do that. So if this is our y-axis, and this is our x-axis, this is your 0, 0. And point 1, 1 is 1 right, 1 up. 1 right, 1 up. It's this. So this is 1, 1. So both curves pass through this point and this point. Let us take the in-between. X is 1/2. This one. So for curve 1, this is curve number 1. When x is equal to 1/2, y is equal to 1/2 cubed. And this is going to be 1/8. So when x is 1/2, y is 1/8. This is 1/4, 1/8 is here. So let me interconnect them. So this is my curve 1. Now the curve number 2, when x is equal to 1/2, what is your y? You have here x squared is y cubed. So y is equal to the cube root of x squared, right? So you solve for y is cube root of x squared. So this is going to be the cube root of 1/2 squared. This is going to be something like 0.63. So when x is 1/2, y is 0.63, 0.5, 0.75, 0.63 is somewhere here. Okay? Like that. So this is going to be your second curve. So in this particular situation, you can use both vertical or horizontal. If it is vertical, we can use that because this is the top, this is the bottom. Also, we can use horizontal because this is on the right, this is on the left, right? Let me use horizontal strip so that it will be different from our video in finding differential area where I use vertical strips. This time, let me use horizontal strip. If I'm going to use horizontal strip, this one, this is a very small change in y, so this is dy. While this one is change in x. It will be x of the right curve minus x of the left curve. The right curve is curve 1, so this is x1. The left curve is 2, so this is minus x of the left curve, curve 2, right? And the centroid of this, take note that the centroid of the differential strip, because this is at the middle of x left, y left, and x right, y right. So this must be x average, y average, right? In as much as we are dealing with dy, our y average will be the same as y, while our x average is x1 plus x2 over 2. Okay? Alright, let's do it. We are to revolve this area bounded by the two curves about the y-axis. So the area that will be generated will be something like this. So the mirror image of this on the other side is this one, right? This one. That is the mirror image. So you revolve this about the y-axis, what you will be generating will be something like this, right? Correct. And the volume of that, according to Pappus Theorem, is equal to the area times the distance traveled by the centroid, 2 pi z. Z is the perpendicular distance of the centroid of area from the axis of revolution. However, in order to solve the volume of the solid of revolution, we need to solve the area bounded by the two curves first. And we also need to locate first the centroid of the area. Then we substitute to the formula, you get the volume. However, we can solve the volume directly without solving the area and the centroid first. It is using the differential volume approach. You will see 8 different formulas in textbooks, except my book, no? As far as this application is concerned, I no longer encourage you to memorize those formulas. Instead, just use this method. If you revolve the entire area, you'll be getting the entire volume. But if you revolve only a differential area, you'll be getting only a differential volume. You get it? So that when you integrate both sides, you'll get the volume. You follow? You get it? Okay, let's do it. Our differential area is equal to area of the differential strip, length times thickness. It's x1 minus x2 times dy times 2 pi z. Z is the distance from the centroid to the axis of revolution. So that is from here to here. Since this is horizontal, it would be x right minus x left. Correct? So it is x right minus x left. The x right is x of the centroid, x average, minus the x left, the x of the y-axis is 0. Or your z is simply x average. Right? So, therefore, our volume is going to be the integral of x1 minus x2 times 2 pi, let me bring it out, times x average is x1 plus x2 over 2, right? Times dy. 2 may be cancelled out. Your volume is going to be equal to pi, the integral of x1 minus x2 times x1 plus x2, it's product of sum and difference, difference of two squares, x1 squared minus x2 squared dy. But in as much as we are dealing with dy, this and this must first be expressed in terms of y. What is x1 squared? From our first curve, our equation is y is x cubed, or x cubed is equal to y. So, therefore, your x is going to be, get the cube root of both sides. This is y to the 1/3, right? So that our x squared of the first curve is going to be y to the 1/3 squared, y to the 2/3. This is x squared of the first curve in terms of y. For the second curve, our second curve has the equation x squared equals y cubed. X squared equals y cubed. We need x squared of the second curve. It's this, right? In terms of y. Substitute this and this for x squared of first curve and second curve. You'll get the volume equals pi, the integral of x1 squared, y to the 2/3 minus x squared in terms of y cubed dy. The only thing we need to add are the limits. This is dy, our limits must also be y. Limits must be y lowest to y highest. The lowest part of this area is here, where y is 0. The highest part is here, where y is 1. So therefore, this is from 0 to 1. Solving the volume equals, so when you integrate this, you'll be getting here 7/20 pi cubic units. You get it? Now, the question is, if we use vertical strip, will the answer be the same? Let's see. Look here. If we will use vertical strip, by Pappus theorem we say that the volume of the solid of revolution is the area bounded times 2 pi z. But in as much as we don't have the value of the area yet and the location of the centroid of this area yet, I will be revolving instead of the whole area, I will revolve only a differential strip or differential area. If I revolve a dA, what I will generate will be a differential volume. Then if I integrate it, integral of d will be cancelled, so we will have the volume of solid of revolution. You don't need to memorize another formula, just the Pappus theorem. Okay? So this is going to be, this time let me use vertical strip. This is a case wherein we can use both vertical or horizontal strip. In most cases, it's only either vertical or horizontal. Okay? Enroll in our course so that you will definitely and specifically understand when to use vertical strip and when you cannot use vertical strips. Okay? Anyway, using vertical strip here, because this is on the top and this is on the bottom, from top to bottom, we can use vertical. So this is a very small change in x, so this is dx. So this is a change in y, so it is y above minus y below. Y above minus y below. The y above is curve number 2, so this is y2. The y below is curve number 1, y1. So that our dA is going to be the area of the differential strip, length times thickness, y2 minus y1 times dx times 2 pi z. Z is the perpendicular distance of centroid of dA from axis of revolution. The centroid of dA is here. By midpoint formula, it is at the middle of the top curve x1, x2, y2, and bottom curve x1, y1. So this must be at the middle, so this is x average, y average. But in as much as we are dealing with dx, your x average is simply x, your y average is y1 plus y2 over 2. Okay? So, therefore, our z is from here to here. This is the axis of revolution. So, this is our z. So, it is horizontal, so it must be x right minus x left. X right is the x of the centroid, x average, minus x left, the x of the y-axis is 0. So your z is just x average, but x average is just x because we are dealing with the x, right? So in as much as we are dealing with dx, everything here must first be expressed in terms of x before we can integrate. So y of curve 2 and curve 1, for curve 1, the equation is y is equal to x cubed. The y of curve 1 is x cubed. No problem with this. What about the curve 2? For curve 2, x squared is y cubed, or y cubed is x squared. Solving the y of curve 2, y is going to be the cube root of x squared. Taking the cube root of both sides, cube root of y cube, y. Cube root of x squared, that is this. So this is the y of curve 2 in terms of x. This is the y of curve 1 in terms of x. We substitute to this. The differential volume of solid of revolution is equal to 2 pi x times y2 in terms of x, cube root of x squared, or this is x to the 2/3, right? So this is x to the 2/3, and then minus y1 is x cubed, okay? Multiplied by dx. So all of this are in terms of x. We are ready to integrate. Integrating both sides, integral of derivative, antiderivative, we will have here the volume of the solid of revolution. The only thing missing here will be the limits. This is dx. The limits must also be x. It must be x leftmost to x rightmost of area bounded. The x leftmost here is 0. The x of the rightmost point is this. So that is 1. So this is from 0 to 1. So solving this now, we will get the volume of solid of revolution equals. So you'll get here 7/20 pi, or that is 1.1 cubic units. It is exactly equal to the volume that we solve or that we get by using a horizontal strip. So whether you use vertical or horizontal strip, basta pwedeng gamitin, you can use it. The result will be the same. No need to memorize the 8 built-in formulas for different situations, whether it is a washer, a disc, or cylindrical shell. So they are all the same. dA times 2 pi z. This is the only formula that you will need for all situations of volume of solid of revolution. You get it?